Welcome back. Let's jump right back into those examples we were working on last time so we can demonstrate a couple other ways that we can use KSP, namely a process called the common ion effect and also a process called determining a precipitate in which we use something called QSP. But let's start with the common ion effect. This problem says, what would be the solubility of AgCl in a solution that has a chloride ion concentration of 0.10? But before we do that, let's table that for a second and let's answer a different question first. Maybe like section off this part of your notes, cut it in half so we can do two things. But let's answer a first question first. What would be the solubility of AgCl? Let me put here, in water, not in this different solution. So there's a method to this. I want you to see how it works. But let's understand that the KSP for AgCl, it's not given here, but the KSP is 1.78 times 10 to the negative 10th. So this is a good little review of last time. Hopefully you remember how to do this. We're going to start by writing the balanced chemical equation because we are just doing this in water. And then we are going to write the KSP expression, which looks like this. It's really easy because it's a 1-to-1 and like that. We're going to set up our ice table and we're going to solve for x. What am I doing? You do this. You know how to do it. Set up the ice table, solve for x, and then we'll talk about it when you're done. Come on back when you're... Okay, so hopefully you remembered how this works. We take that value, we plug it into the KSP, we just solve for x. So I can get 1.33 times 10 to the negative fifth. I should put my units here. This is moles per liter in H2O. So that's cool, but now let's compare what that looks like if we were to determine the solubility of this substance in a different concentration. So let's, I'm going to clear this off a little bit. And like I said, hopefully you've sectioned off a little space. I'm going to put this over here so I can refer to it later. But let's look at this step now in a different concentration of a different solution. So before we were just in water. But now let's see what happens if we have something where we're not in just water. So let's write this again. I should have probably left this alone. And now I have Ag plus and Cl minus. Set up my ice table. So remember, in this situation, we are now no longer in just water. We are in a solution of chloride ion. And maybe that chloride ion came from like NaCl or something. So then we had this solution of sodium chloride that we dissolved. Now we're trying to dissolve AgCl. And this is where that Cl minus is coming from. But we have a concentration of about 0.10. So where is this problem different than the water situation? Well, the setup is pretty similar, where we know that we're going to dissolve by some amount x, which means that these are going to increase by some amount x. Well, let me not get ahead of myself. But let's think about what our initial values must be. We should still have 0 of the silver, but do we have no chlorine present in the solution at the beginning? Before we didn't have any chlorine present in the solution because it was water, but now we have this 10 from the ion concentration. It's already in solution. We dissolved it previously, and now we're trying to dissolve something in there again. So now it's a little different. Now we do the x's. This time we're going to have 10 plus that x. So then I get 0.1 plus x. Now we're going to take these, we're going to plug them back into our KSP. So I got 1.78 times 10 to the negative 10th. And that's going to equal x times 0.1 plus x. So let me ask you a question here. Do you want to do this problem the easy way or do you want to do this problem the hard way? I'm sure on the other side of this, you're probably thinking, yeah, let's do it the easy way. You probably might notice that if I'm looking at this math that's here, what's going to happen is I'm going to have to distribute out the x, and I'm going to have a quadratic on my hand because I'm going to have like x squared, you know, and then some other values that come from the factory. And I don't want to have to do that. So what I'm going to do is I'm going to do a technique where I'm going to assume X is small. And by X, I mean this X right here, or this X. I'm assuming that that X value is small. Why can I do that? Well, let's think about it. This value here is how soluble it is, right? If you think about it, like it's 1.78 times 10 to the negative 10th. That's how soluble something is. If we were to calculate this value and find a value for X, there's probably an assumption that that X value is going to be really, really, really small. And let's say that we have a really small number, like let's say it's like 0.00000000008. Really, really small. If I add 0.10 to 0.000000008, what am I going to get? Well, after I round, I'm just going to get 0.1. The rest of it doesn't really matter. It's too small. So if I assume this, I can actually remove that X. This gets removed. So then my new expression is 1.78 times 10 to the negative 10th equals X times 0.1. And now this becomes much easier math. And when you calculate this, you should find that you get 1.8 times 10 to the negative 9th. And that's in moles per liter in, and I'm going to say in a solution of Cl minus. So keep that in mind as we're working forward. And the only time I can do this is when my K values are really, really small. But for the most part in our course, that's always going to be the case. Now, whenever you assume X is small, you got to prove it. So now let's go back and let's add this number to X and see if it works. So 0.10 plus 1.8 times 10 to the negative 9th. After I round it, that's just 0.10. So yes, that's good. That means it's fine. We have to check it. It's just something that you want to show. Even if you want to label it real quick, you just say check. And we got to check it. Okay? If that wasn't the case, then it would be wrong. But like I said, for the most part, in this course, it's always going to be correct. So let's compare this value, the 1.8 times 10 to the negative 9th, with this value. Notice that when we add an ion, what's called a common ion, to our solution, we actually decrease the solubility. This is because this ion in solution pushes the reaction back towards the reactants. And we'll talk a little bit more about that later as we keep going. But it shifts the reaction back towards the reactants because we are increasing the concentration of Cl minus. Think back to rates. If I increase the concentration of something, I increase the rate of that reaction, which means I'm increasing the rate of the reverse reaction, which means I'm making more insoluble salt. So that means that I'm decreasing the solubility, therefore increasing the precipitate. That's how it works. This is what's called the common ion effect. It's just something to keep in mind. All right, let's try another one. This time we're going to look at Ag2CrO4, which means silver chromate. And you're going to be working on this one. I want you to find out the solubility of this in a common chromate ion solution. You're going to need the Qsp, which is not given in the problem for some reason, but it's 1.12 times 10 to the negative 12th. Work through the same process that we worked through before. Make sure that you do not forget to write your balanced chemical equation, write your Qsp. Be careful of the ratios. Don't forget that you have a concentration of chromate already in solution, and then try and find out what the solubility is. You don't have to do the water comparison this time. Just find the solubility in the ion concentration. You don't have to find the solubility for water. If you want to, just practice you can, but you do not have to. Come on back when you're done. Okay, hopefully this is what you got. Common mistakes that I could see you making is that you forget to do the balanced chemical equation. Don't forget that you have 2 silvers in solution. So that has to follow along with your ice table. It also has to be included here. So make sure that when you plug in, you do 2x squared. And then you always have to say that you're assuming x is small. You can't just remove x. So we assume x is small. It gets rid of this x here. Then we have just our Qsp times 4x squared times 0.05. And then we get x is 2.3 times 10 to the negative 6. And that's the solubility. Got to check it. So go back and check it. It just takes a second. Because it's usually going to be true. Got to show that proof there. All right. So that is what's called the common ion effect. Let's keep going. Let's look at something now called Qsp. Now, before we jump into this, I'd like you to take a second and consider something for me. I'm going to do it over here. I want you to consider, and you can add this in the margins or something if you want, but I want you to consider the reaction of, let's see, lead nitrate and potassium iodide. And if these were to double replace, then we would get potassium nitrate and lead iodide. And I want you to ask yourself, do you think a precipitate would form? Based on our solubility rules, lead iodide should be a solid. But does that mean that a precipitate forms? Well, let's make just a really, really extreme assumption. Let's assume that in solution, I only have one ion of lead and one ion of iodide. If I were to make this solution, do you think that we would see a precipitate? No, probably not. There's probably not a high enough concentration for that precipitate to form. So even though something is insoluble, that doesn't mean it always forms a precipitate. If the concentrations of those ions are not high enough, no precipitate will form. And this is what's called Q. So we solve this using what's called Q. I kind of misspoke there. So we use a technique called Qsp to find this, and I'll show you how this works. So let's first start with number 9 by calculating the concentration of each ion after we mix. So this is a dilution problem. We are given the concentration of each ion before we mix them. We want to calculate the concentration of each ion after we mix them. So go ahead and give this one a shot. You can probably do this on your own. Go ahead and pause and calculate concentration. Like I said, this is a dilution, so it's like an M1V1 equals M2V2 sort of thing. M1 is given to us, V1 is given to us, M2 is what we're looking for, V2 is the combination of the solutions, so 30 and 25. Give it a try and come on back when you're finished. Do it for both. See you then. Okay, so now we have those concentrations before, or excuse me, after they have been mixed. So again, it's a dilution thing. I just set up the dilution. I'm solving for M2. So let's determine if a precipitate will form. When we want to determine if a precipitate will form, if you ever see that language, I want you to think about how we're going to use what's called Qsp. So Qsp works the same way as Ksp does. So let's first start by writing out our balanced dissociation equation. And the only reason why we write out the balanced dissociation equation first, we don't have to really set up an ice table this time. We just need to set up our dissociation equation so we can understand how to write the Qsp expression. Qsp is written just like Ksp is, where it's the concentration of the products over the concentration of the reactants. We want to make sure that we don't have any sort of different ratios, like a 1-to-1 ratio or anything. Now we just take the concentrations that were given at the beginning. I'm going to actually kind of just I'm going to swap these here. You're welcome to flip-flop them or keep them how you did them. Gonna move this one like this. That's a little better. Okay, so now we're just gonna plug in the values that we found before. So this is 9.09 times 10 to the negative 4th, and this is put a decimal where I don't want one. 1.09 times 10 to the negative 3rd. And when we multiply these out, we should find that Qsp is 9.91 times 10 to the negative 7th. Cool. So what does this mean? Well, let's make ourselves a little box here so we can give ourselves a little more information. So what we're doing is we're comparing Q to K. So if Q, I'm going to put this in here. If Q is equal to K, then we're at equilibrium. And that means we're probably saturated, which means we probably won't see a precipitate. If Q is less than K, no precipitate will form. It means that the concentrations are not high enough for a precipitate to form. But if Q is greater than K, there will be a precipitate. So that's really all it is. We just compare this to our K value. Sorry, my noodle's in the way there. So if I'm looking here, this is not as big as my K value. I mean, they give me the K value at the beginning. They say it's 2.4 times 10 to the negative 5th. So this is absolutely not as large as my K value. So I'm going to have to state that. I say Q is less than K. I'm going to use math here. I'm going to use the dots, which means therefore. And I'm going to say no. I'm going to abbreviate precipitate with PPT. Will form. Just like that. That's how you would answer. So use that math. Those dots just mean therefore. It's like a proof. So no precipitate will form. Go ahead and try this one on your own. The process is pretty much the same, except you're not going to have a 1-to-1 ratio, so it's going to be a little trickier. Go ahead and find the concentrations after mixing first. It's just like last time. And then determine if a precipitate will form. Come on back when you're finished. All right. Hopefully this is what you got. If you run through the concentration calculations, you should get 0.0060 for lead. You should get 0.011 for bromine. I write out my dissociation equation real quick just so I can find that I have this 2 here. It's really important that you do that because I need to put that 2 there. If you forget to do that, you might get a wrong Q value, which means you might come to the incorrect conclusion. So if I do this correctly, I find that I get a QSP of 7.3. I compare that to the KSP given at the beginning, and then I say whether or not it's large or small. In this case, it's too small, so yeah, no precipitate will form. And that's it. So it's really just the same process. It's almost even easier because these usually don't require ice tables. But even if they did, it wouldn't be that tough. We would just be able to put the ice table in before we calculate the QSP. And that's it. Next time we will talk about Le Chatelier's principle. We'll see you there.